All right, we're going to do another paper one. This is 2013. You can find this on studentshare.com. That's where I found it, and download a copy so you can have it for yourself. Okay, so let's go. I'm going to try and talk faster in this video, and you can feel free to pause it or back if you need to see the answer or had an explanation for a question. All right, number one, reading of an ammeter used to measure current in an electrical circuit is shown. Okay, so we're looking at a simple linear scale, and we're being asked to find the reading on the scale. So at first glance, you might think, oh, that's 2.5, 2.6. I'm correct. The misconception that a lot of people have is that this is 3. Okay, because we look at 2 and then we say, okay, 3 must be between 2 and 4. Okay, number one, the reading of an ammeter used to measure current in an electrical circuit is shown. What is the reading on the ammeter scale? So at first glance, you might say that it is 2.5, 2.6. Why is that not correct? We got to look at the whole scale, okay? We got to look at all the divisions. This can't be 2.5 if the next whole number is not 3, but 4. Okay, that means that this unmarked division right here is 3. Okay, so you want to first make sure you fill in the missing division so you can know how you're counting. Okay, so this is 0, 1, 2, 3, 4. That'll be 5. And that should be 6, 7, and 8 actually. Okay. So okay, so you want to fill those in. I do realize that the rest of this scale on this side is not correct, because if that's 4, then the next one should naturally be 5. And so this should actually say 6, that should say 7, and this should say 8. Okay. I'm being a little finicky here. That doesn't actually affect our answer because our pointer is here, but still, okay, good to be diligent. So what this reading is going to be 3.2. Okay, so 3, 3.2, 3.4, 3.6, 3.8, and then gets us to 4. So
you have 5 minutes for the end of this examination.
the answer is 3.2 amperes. Number 2, physical quantities can sometimes have more than one unit. Each line of the table shows 2 possible units for a physical quantity. Don't forget the rest of the question down here. Which row in the table gives units for rate of doing work? Rate of doing work. That is, what are we talking about? We're talking about the quantity power. Okay, so power is measured in watts, and the definition of a watt is 1 joule per second. Remember, power is equal to energy divided by time. So joules per second. So our answer is D. Number 3, which is the following represents a second-class lever. Okay, so we're looking for the machine that puts the load in the middle. That would be this one here. Okay, you can check all the others. The load goes at the end for each of those. Okay, first class lever has the load between on either end of the lever. Second class levers have the load in the middle, okay, between the fulcrum and the effort. So fulcrum is here, effort is up here where you hold it. Number 4, diagram shows a picture of a submerged submarine, which pair of forces must balance to keep the submarine submerged at a constant depth. Okay, depth means that we're interested in the vertical forces being balanced. Okay, if one was greater than the other, if X was bigger, then it would rise. If W was bigger, then it would fall. Okay, so in order to keep it not rising or falling, the vertical forces must be balanced, and those are forces X and W. So A. Number 5, a trolley is used to carry a box of weight 800 newtons. The weight of the trolley and the box together is 1,550 newtons. If the gravitational force per unit mass is 10 newtons per kilogram, what is the mass of the trolley on its own? So first we have to find the weight of the trolley on its own by dividing the weight of by subtracting the weight of the box alone from their combined weight, which is going to give us 750 newtons. And then to find the mass, we're going to use the relationship mass is equal to weight over gravitational strength. So we're going to have 750 newtons divided by 10 newtons per kilogram, which is going to give us a mass of 75 kilograms. So our answer is A. Number 6, a measuring cylinder contains 75 cubic centimeters of water. A gold nugget is gently lowered and fully immersed in the water. The new volume of the water and the nugget is found to be 90 cubic centimeters. If the mass of the gold is 45 grams, what is the density of the gold nugget? Okay, so 2 relationships we need to use. First, we need to recall that density is equal to the mass of an object divided by its volume. And we're finding volume by displacement here. So the change in volume when the measuring cylinder was added, 2 minus V1 is going to give us the volume of the object. That is going to be equal to the final volume, which was 90, minus the initial volume, 75, which is going to give us 15 cubic centimeters. Plug that into this relationship over here. Call the mass is 45 grams. There's no need to convert to kilograms or to cubic meters. As long as you have grams with cubic centimeters, you're good. That's an acceptable unit. And when we work that out, 45 divided by 15, we're going to get 3 grams per cubic centimeter. So our answer is D. Okay, so number 7. 2 students, Sam and Paul, conduct simple investigations on the reflection of sound waves. Sam and Paul stand 60 meters and 80 meters away from a wall, respectively, as shown. If the speed of sound in air is 340 meters per second, how long after seeing Paul clap his hand will Sam hear the echo of the clap? What's important to remember here is that the receiver is Sam and the source is Paul. So we want to know the distance that the sound travels from it leaves the source till it reaches the receiver, okay? So that would be the 20 meters that it travels from Paul past Sam plus another 60 meters till it hits the wall. So that's 80 meters in total to go to the barrier, okay? And then it has to bounce back. And when it bounces back, it's going to travel another 60 meters until it reaches Sam, and he hears it. Sam is the receiver. So we're going to use our equation for speed, and we're going to transpose that for time because we want to know how long. So time is equal to distance divided by speed. The total distance is going to be the 20 meters from Paul to Sam plus the 60 meters from Sam to the wall plus the 60 meters back to Sam after it bounces off of the wall, okay? All divided by 340 meters per second. Simplifying, that total distance is going to be 140 meters divided by 340 meters per second, and that's going to give us 0.41 seconds. You can pause it and check your answer. Make sure you get the same thing. Our answer is going to be C. All right, number 8. Which is not true of the image formed in a plane mirror? So in other words, which one of these is not a characteristic of a plane mirror? Okay, when you look in a plane mirror and you hold up your left hand and you look in the mirror, you're actually going to see that your image, the image of your hand, is inverted, okay, laterally, which means it's left, right, reverse. For a plane mirror, when you look in a mirror, you are not bigger or smaller. Your image is not bigger or smaller than you, so you're the same size, okay? When you move closer to the mirror, you notice you see the same effect with your image. So the mirror image, the source, the object is always the same distance in front of the mirror as the image is behind the mirror, okay? And that should give you a little clue right there. Whenever an image is formed behind the mirror, it is a virtual image. So plane mirrors don't give us real images because we can't take them with us. We can't put them on a screen. So the one that does not belong is going to be B. Okay, all the others are true, are characteristics of plane mirrors, except real. So they don't give real images, they give virtual images. All right, number 9. Which of these equations illustrates Newton's second law of motion? Newton's second law of motion tells us that the total or the net force that acts on an object is equal to the product of its mass and its acceleration. Okay, the equation that describes that is that one right there, A. The distance time graph, number 10 now, shows the movement for 4 cars, A, B, C, and D. Which car is moving the fastest? Okay, so for a distance time graph, the slope is given by the speed. Okay, so the steeper the slope, the speed is given by the slope. So the steeper the slope, the greater the speed. And you can even look at when you just think about what that means. If you're going faster, then that means you cover more distance in a shorter amount of time. Okay, so at this point right here, if we just draw a line down, we can see that this point is the highest on the distance axis. So that means the most distance has been traveled by A, and it also has the shortest time. Okay, this one here, we have a short amount of distance covered, so it didn't go very far, and it took very long to do that. So this would be the slowest speed right there. Okay, steeper the slope, the greater the speed for a distance time graph. So our answer is A. Number 11. What is the energy change as an object falls through the air, assuming there is no air resistance? Okay, so there are two main types of energy. We know an object can either have energy due to its shape or position, and that would be potential energy. Okay, shape, that would give us elastic potential energy if an object is stretched or compressed, or if an object is some height off the ground, then it will have gravitational potential energy because it has the potential to move or to do work due to the force of gravity acting on it. The other type of energy is kinetic energy. Once an object is in motion and it's moving, it has kinetic energy. Okay, so if you think about what happens when an object falls, before it starts to fall, when it's at its initial position, some height off the ground, all the energy it possesses is gravitational potential energy. As soon as it starts moving and it gets lower and lower and lower, closer to the ground, the amount of gravitational energy that it has decreases and the amount of kinetic energy that it has increases because objects fall at the all right, so as an object falls through the air, it undergoes an energy change from gravitational potential energy initially to kinetic energy. Okay. And it's important to remember here as well that at any point in time when an object is falling, the total sum of the energy that it has is going to be the sum of its gravitational potential energy and its kinetic energy. Okay. All right, number 12, which physical quantity has both magnitude and direction? We're asking which one is a vector, okay? Which one can we ask the question, which way and how much, and get an answer for both? Okay, and that would be the gravitational force weight. Mass, speed, and time are all scalars. They have no direction, only magnitude. Number 13, why do computer monitors have holes or slots in the backs of their cabinets? Okay, to allow for some transfer of heat. Yes, that's correct. But which method? There are three ways that we can transfer heat. We can transfer heat through direct physical contact of materials. That's conduction. Okay, so that's not what's happening here. Convection, that's when we have heat moving through a fluid and the entire fluid is moving with it. That's not what's happening here. Reflection of heat, okay, that requires us to have some kind of shiny surface. That's not what's happening here. What we're looking for is heat transfer through a vacuum or through the air, through space. And that's what's happening when heat is allowed to leave the slots of the back of the cabinets. Okay, so C will be our answer for number 13. Number 14, the diagram shows water rising in a glass tube. What causes this effect? So the instrument that we're looking at is called a barometer. Okay, and sometimes you might see this with mercury in it. And the purpose of this instrument, what its function is to measure how much pressure is being exerted on the earth by the atmosphere. Okay, so when that water is open to the elements, if atmospheric pressure is high on that particular day, then the pressure exerted on that surface will be great, and it will push it down, forcing water up into that glass tube. And that glass tube is empty. There's nothing else in there. There's no air to take up space and stop the water from moving up there. So it can very accurately show when there is a change in pressure. So if the water is rising, then that means that there's an increase in pressure. Okay, increase in atmospheric pressure, to be specific. So the cause of this effect is the presence of atmospheric pressure. Okay, increased air pressure in the glass tubes, not correct, because there is a vacuum in that tube. If there was increased air pressure in the tube, then the air would expand and push the water out. And so we would see the water level rising outside of the tube instead of inside. Okay. Decreased atmospheric pressure would cause the water level to drop. Okay. Because if there is nothing pushing on it, then we won't see that rising in the tube. All right. Number 15. Smoke particles in air are examined under a microscope. They move about and make frequent haphazard changes in direction. Why is this seen? Okay, so this was a very important discovery, and this is at the forefront of our knowledge of atoms and gases and how they behave. Okay, so what's happening is the random movement of air molecules. Nothing is causing them to move. This is just a characteristic of gas particles. They move around randomly, and when we put something in their way, we find, like the smoke particles, we find that they will bounce into them and collide with them. So the things that we can see, the smoke particles that have no energy, they haven't been supplied any energy, or there's no wind blowing them or causing them to move. So their motion is due to colliding with something else that is moving, which is the air particles that we cannot see. Okay, so our answer is going to be D. They collide with invisible air molecules. And that's called Brownian motion, by the way, not to be confused with diffusion. Okay, Brownian motion describes the random movement of air molecules, okay, just in their natural state. No energy is being supplied to them. This is just what they do naturally. Now, diffusion occurs when we have
For the end of this examination, we will tell.
diffusion occurs when we have an excess of gas molecules or any particle in one area. What they tend to do is spread themselves out, and we get a movement from a highly concentrated area to a lower concentrated area until the distribution is even. Okay, so that process of moving from a crowded place to a not crowded place for particles is called diffusion. Okay, not to be confused with Brownian motion. Number 16. Marcus cycles at a steady speed of 6 meters per second for 2 minutes. What is the average distance covered by Marcus? Okay, so automatically your mind is going to go to this formula. Distance is equal to speed multiplied by time. And we're told that the speed is 6 meters per second. Okay, to use this formula, any values of time must be in seconds. We're given our time period that Marcus was cycling over as 2 minutes. Okay, we have to convert that into seconds by multiplying by 60, because 60 seconds is equal to 1 minute. Okay, so simplifying, I'm going to get 6 multiplied by 2 times 60, which is 120. 6 times 120 is going to give us, which is going to give us 720 meters. Okay, and so our answer is right here. Our answer is D.